and we had already started last time broadbanding by local feedback. We continue this discussion today. The circuit that we had considered was simply a single transistor amplifier with a feedback from the collector to the base through this resistance RF. Obviously, this is a shunt feedback, but we did not use any property of feedback. We wanted to analyze it directly. This we had drawn last time, and the equivalent circuit of this was drawn like this with several components combined together. Z pi, for example, takes care of RS, the parallel combination of R pi and C pi. That is why Y pi is equal to this, and in addition this quantity Gs plus G pi we had represented by G pi prime, and Y mu is the inevitable C mu between the base and the collector and the parallel connected RF. Therefore, Y mu is Gf plus S C mu. And then we had tried to calculate the transfer function. The transfer function here is V0 over I sub S. We call that the dimension obviously is that of impedance, and therefore we call it Z subscript capital T for transfer. Okay, that is the transfer impedance ZT equals V0 by Is, and we derived this to be of the form 1 over C pi S plus Z divided by S squared plus B1 S plus B0. Obviously, this can be written in the following form: Z over C pi B0, this is the mid-band gain, and then 1 plus S by Z, 1 plus B1 by B naught S plus S squared by B naught. Obviously, if you put S equal to 0, this is the mid-band gain. Z is the 0, C pi B naught. The values of these constants were given earlier. Z is simply equal to Gf minus Gm divided by C mu. B1 is equal to G pi prime, which we have defined earlier, plus Gm plus Gl divided by C pi plus Gf plus Gl divided by C mu, and B0 is a longish expression, Gl Gf plus G pi prime plus Gf G pi prime plus Gm divided by C pi C mu. Let us not get lost in the complication of these expressions. These come by algebra, but nevertheless you keep this, because in order to do a numerical design or analysis, you shall require these formulas. Now, we had found out also the output and input impedances of this configuration, and it came out, well, first was the mid-band gain. The mid-band gain, which is Z by C pi B0, mid-band gain, okay, Z by C pi B0. This was exact expression you can find out, but we had shown that this is approximately equal to minus RF, under the following conditions: that Gm is much greater than Gf, beta is much greater than 1, and I think that is all. Beta much greater than 1, which means that G pi prime is approximately equal to, G pi prime was approximately equal to G pi, which means that Rs is much larger compared to R pi. Agreed? Okay. These are the assumptions under which RT is equal to this, and we had also interestingly found out that if we calculate V0, V0 by Vs, okay, V0 by Vs, then this is equal to minus Rf divided by Rs, okay, which was comparable to an op amp connected in the inverting configuration. Okay. Last time we also derived an expression for the output impedance Z out. Z out is to be obtained by open circuiting I sub s, connecting a voltage generator at the output without RL. Z out is the impedance seen by RL, okay, and calculating the current, and this was found out to be Z pi plus Z mu divided by 1 plus Gm Z pi, and the midband value R out, which is equal to Z pi would be simply what? R pi prime. Z pi is the parallel combination of R pi, Rs and C pi, plus midband value is Rf, 1 plus Gm R pi prime, and this is approximately equal to Rf divided by beta. R pi prime is approximately equal to R pi, Gm R pi is beta, and beta is much greater than 1 plus 1 over Gm. Okay, and this is a low value. Output impedance is low because the feedback is shunt. At the output the connection is shunt. It is a voltage sampling. Okay. Similarly, we had found out that the input impedance Z in, which is obtained by connecting a voltage generator at the input and finding out the current, Z in was equal to Z pi parallel Z mu plus RL divided by 1 plus Gm RL, and the midband value was equal to R pi parallel Rf plus RL, Z mu midband value is Rf, divided by 1 plus Gm RL, and if you carry out the algebra you can show that this is approximately equal to R pi Rf plus RL divided by beta RL. Under what condition? Beta much greater than 1, so that beta plus 1 is equal to beta, and the other is that beta RL must be much greater than R pi plus Rf. Okay, and this is also low because of a shunt connection at the input. Okay, this is also a low value because of shunt connection at the input. And typical values we had taken, we recall this example because we shall carry this example through. Rf was 10K, Gm was 0.04 mho, beta was 50 and RL was 1K. Under these conditions our R out was simply equal to 225 ohms approximately, and R in approximately was 235 ohms. These are comparable values. They are low values. Okay, they are low values. This low value of the input and output impedances is very important, as you shall see when you use overall feedback or you use more than one stage of feedback. Then the matching between the preceding stage and the succeeding stage will require that you use series succeeding shunt. You understand? If the output is shunt connection, then the matching we require a series connection at the input, so that the input impedance is much larger. Okay. Now, as I said last time, we were left with the $1 million question of calculating FH, the high frequency, the 3 dB point. Okay. This is the motivation. We wanted to broadband the amplifier, that is increase FH as much as possible. Now, if you recall, the transfer function is not very complicated. It is some midband value, let us say RT midband value multiplied by 1 plus S by Z, 1 plus, what was it, B1 by B0 S plus 1 by B0 S squared, and therefore omega H shall satisfy the equation, I don't have to write anything else, putting S equal to j omega, taking the real part imaginary. I can do it by inspection. You see, what will happen is 1 plus omega h squared by z squared, I am taking the magnitude squared, divided by 1 minus omega h squared divided by b0 whole squared, real part squared, plus b1 by b0 omega h whole squared. This should be equal to? No. Should be equal to? Half. That's right. Because the mid-band gain has been taken away, and the magnitude should be 1 by root 2, magnitude squared should be equal to half. So what you have to do is to solve for this equation. Obviously, this is a quadratic equation of in omega h. Quadratic. Quadratic means degree 4. Omega h squared squared, but it is a quadratic in omega h squared. Therefore, it is a quadratic in omega h squared, and therefore, if you are very fussy, solve the quadratic. It's not very difficult. Solve the quadratic. Okay, quadratic in omega h squared, and therefore it can be solved. But if you are lazy, and or there is a C0 also, then obviously the degree of the equation to be solved would be, if there is another capacitor, then the degree will increase by 1. Therefore, it will be a cubic equation in omega h squared, and a cubic equation has to be solved numerically. The analytical solution is not convenient. You cannot write a formula. You go through several algorithmic steps. So it would be good to consider the method, the alternative methods that are available. One of them, of course, is the application of the Miller technique. Now, if you recall, the equivalent circuit was IS technique 1. So, technique 1 is solution of the equation, exact equation. Technique 2, that is due to Miller. Okay. Technique 2, what we do is Z pi. Then since Z mu is the culprit, we reflect it to the input and also to the output. Now, if we reflect it to the input, what would this impedance? It is better to find the admittance. The admittance would be Y mu multiplied by 1 minus gain. Now, 1 minus gain, and gain is minus GMRL, so 1 plus GMRL. Is the point clear? No? Okay. If it was a C mu, how do you reflect this? It becomes C mu 1 plus GMRL. And therefore, this admittance S C mu reflects as S C mu times this. Instead of S C mu, I have a parallel connection of S C mu and RF. And therefore, the admittance is GF plus S C mu. Therefore, this shall be replaced by Y mu. Is the point clear now? Instead of a pure capacitance, we have a capacitance in parallel with a resistance. So, you take the total admittance and reflect this as Y mu 1 plus GMRL. Yeah.
In case of Miller's approximation,
Yes.
what we do is that the gain which is being written over here, GMRL,
Is the mid-band gain. Yeah. This is the approximation.
so we assume the mid-gain.
If you had found out the exact gain and put it here, then it would not have been Miller approximation. The word approximation has to be crossed out. But if you put the exact gain, your life will be miserable, because this will be a complex quantity. Okay? Life will be miserable. Anyway.
Excuse me, sir.
Yeah.
So when we were doing the analysis beforehand, we were using impedances and voltage source, and current and admittances.
Doesn't matter. Between this point and this point, whatever the gain is. You know, Miller effect is, you have an intermediate part of the circuit in which you know the gain between port 1 and port 2. Then any impedance that is connected here can be reflected to the input through V2 by V1 and to the output through again V2 by V1. Okay, so this current source or voltage output, they have no place. There is a bridging impedance which you don't want to take into analysis, and therefore you reflect it to the input, reflect it to the output. That's it.
So, but putting in RF will change even the midband gain.
Putting in RF would even change the midband gain. This is quite correct. We ignore that. We keep our eyes closed. Okay. Now, then we have at the output circuit, what do we have? We have GMV, then RL. What is it reflected as? This is V0. What would be this impedance? It would not be Y mu. It would be Y mu 1 plus GMRL divided by GMRL. That is correct. And it is equal to Y mu only under the condition, no, 1 minus gain. No, 1 minus gain divided by gain magnitude. Gain magnitude, yes. Now, it would be equal to approximately equal to Y mu if GMRL is much greater than 1, which we assume. Alright. I am illustrating this, although this is not needed because a quadratic equation can be solved. But I am illustrating this to get an idea of the general Miller effect, not just a capacitance. Let us have any impedance, then how do they reflect? Now, if you expand this Miller equivalent, you shall have IS. Let us go to Z pi. What was Z pi? RS, R pi. You will understand why I am expanding this, because I want to calculate the time constants. RS, R pi, and then we had a C pi. The Miller Y mu 1 plus GMRL gives me a capacitance which is C mu 1 plus GMRL, and a resistance. What would be its value? RF upon 1 plus GMRL. You see, it would be reflected as a low impedance now, and it might become comparable to RS and R pi, and therefore it has to be taken into account. Clear? Okay. Then we have the GMV. This is V, GMV, then RL, and since the reflected impedance on the right hand side is simply Y mu, I shall have an RF and C mu. I am assuming that GMRL is much greater than unity, V0. I must emphasize that this is not an exact circuit. It has imperfections in many ways. Nevertheless, it gives, we will show that it gives reasonably good values. Okay, this is my equivalent circuit. Now, in order to analyze this, yeah.
If we take RL as RL parallel RF, would it
Right.
be a better approximation or worse?
Would it be a better? Perhaps. Perhaps.
So you're asking whether it would be better or worse?
I can't answer this question now, because what you have to do is to take the midband equivalent circuit and actually calculate the midband gain. It would not be GMRL obviously, because RF is going to affect it. You see, there is a potential division between RF and RL. But unfortunately RL is not a pure resistance, it is paralleled by a GMV. You have to make an analysis. Okay. Now, therefore, now it is not a problem. We have two capacitors, and we can apply the method of open circuit time constants, or we can analyze this exactly. The two frequencies, two critical frequencies, which the two poles which will affect the the overall FH, obviously is the parallel combination of C pi and this C pi and this capacitance. So we shall have one time constant as C pi plus C mu 1 plus GMRL multiplied by RS parallel R pi parallel RF divided by 1 plus GMRL. Let us call this time constant as tau, what shall I call? Tau I, input time constant. This will obviously give rise to a factor of the form 1 plus s tau I, okay, or 1 plus s divided by omega I, where omega I is 1 by tau I. And the output time constant tau naught is simply equal to C mu times RL parallel RF. And your FH, the high frequency value, high frequency 3 dB point would be simply 1 over, don't forget the factor 2 pi, 2 pi tau I plus tau naught. Alright, that is it, as simple as that. Of course, it is an approximate figure. Let us take a specific example. The example that we had been considering the example that we had considered, we required some extra values. Let's have C mu equal to 2 puff, C pi equal to 25 puff, RS was not given earlier, it was not required, RS is 2.5 K, let us say, RF was given as 10 K earlier, RL was also considered earlier 1 K in calculating the input and output resistances. The GM for the transistor was 0.04 mho and beta equal to 50. Then if you substitute the values, you get tau I as equal to 20.2 nanoseconds. Nano means 10 to the minus 9. Okay. And tau 0 calculates out as 1.8 nanosecond, which is less than 1/10 of tau I. Therefore, the input circuit dominates FH. Therefore, FH is approximately equal to, you can easily ignore this, or if you don't want to ignore, you add it up, okay, 1 by 2 pi tau I, and this calculates out as, I don't know which I calculated, right? The approximate value or tau I plus tau naught, but my result here is 7.88 megahertz. 7.88 megahertz. On the other hand, now if it is to be a broadband, obviously if RF was not there, what does it mean? RF is infinity. If RF is infinity and you recalculate the whole thing, if RF is infinity and you recalculate the whole thing, then you get FH as equal to approximately equal to 1.1 megahertz. So that the broadbanding is by a factor of 7, almost a decade, factor of 7. But of course, the sacrifice is that you have to sacrifice in gain. Okay, right.
So the approximation of Miller's can it be used to evaluate the output difference?
Approximation of Miller?
Can it be used to evaluate?
No, cannot be used. No.
Then how would we use it to evaluate the output time constant?
Output time constant is okay. You see, Miller only comes into effect, we have to take help of Miller because we want to find the 3 dB points, okay, the poles of the transfer function. Now, as far as the output is concerned, it does not see only RL, RF and C mu. No. It does see, we did not take account of Miller in the reverse direction. If we had, what you are saying would have been correct. Miller, for example, can be used for input impedance, that is not a problem, but not in the, you see, we considered the transistor to be unilateral, and therefore we considered the gain V2 by V1. If we consider V1 by V2 and reflect it the same way, yes, we will get what you wanted, but we don't do that, because usually the output impedance calculation is much simpler than FH calculation. FH calculation requires a set of node equations, loop equations and matrix inversion and things like that. Okay, so we want to do it by inspection. Miller said, okay, I will help you, but of course you have to give a leverage. I mean, you have to relax on the accuracy requirement. Technique 3 is the method of open circuit time constants, that is without taking Miller, open circuit time constants. Now this requires a bit of calculation, because you will have to calculate the equivalent resistance seen by each capacitor by open circuiting the other capacitors. Okay, recall the equivalent circuit. The equivalent circuit was IS, then R pi prime, then now there are some tricks which I am going to, I have already done this, but I am going to repeat, because you will get such calculations very often, and then you should be able to do it very quickly without even writing the loop equations and node equations and things like that. I will show you how. I will show you, I will indicate to you, because they are not universal. You have to identify this circuit, okay, and a little bit of ingenuity, of course. Let's draw the exact equivalent circuit in terms of its expansion, because we want to isolate the capacitors R mu. Then this is GMV RL and V0. Now in this circuit, if you want to calculate, let's say, the resistance seen by C pi, then you have to open circuit C mu, and you have to open circuit IS also. If you do that, then the equivalent circuit for calculation of R pi, that is the resistance seen by C pi, I am drawing it from the equivalent circuit. We shall have R pi prime here, okay, then an RF, GMV and RL. All right. It is the resistance seen between these 2 points. One of the tricks is that if you can identify a series resistance or a parallel resistance, isolate that. Obviously, R pi would be equal to R pi prime parallel what is seen by this circuit. Okay, don't include this, then you have to write an extra term. Okay, if you recognize this, then you open this R pi prime parallel, let's call this as R pi prime. Then you calculate R pi prime, which is obviously a very simple task, and therefore the result is R pi prime parallel RF. This we have done again and again, RF plus RL divided by 1 plus GMRL. If you don't remember the result, well, it's not too bad. What you do is, this is V, convert this mentally into a Thevenin equivalent. So you get GMRL V, right? And therefore the equivalent source is V plus GMRL V, and the equivalent resistance is RF plus RL. All this can be done mentally. All right, it's not too complicated. Let's look at C mu, R mu, the resistance seen by C mu. Okay, the equivalent circuit is the following. Between these 2 points, there is a resistance RF, C mu in parallel with RF. Then you have, from here, you have R pi prime, and from here you get GMV and RL. What you have to do is to connect a source here, V, let's say this is the polarity, and calculate the current I. Another simplification, you notice that the source V is in parallel with RF. So you could as well R mu would be RF parallel R mu prime, and you take off RF. The circuit becomes now much simpler, and you can replace this by the Thevenin equivalent. Then it becomes a single loop, and you can calculate the whole thing mentally. Can I repeat? I notice that R mu is a parallel combination of RF and the rest of the circuit. So I get rid of RF. I write R mu as equal to RF parallel R mu prime where R mu prime is obtained by omitting this. Then you have a source, a resistance, and then a parallel combination of a current generator and RL, and therefore you can replace this by a Thevenin equivalent.
That's not GMB.
V pi. Okay, and where is V pi? That you must not. Don't do anything to destroy this. Okay, if you make a transformation to destroy this, then of course your circuit calculations will go haywire. So you must not destroy this. This is V pi. Then it becomes a simple single loop circuit and you can calculate. The result is R mu is RF parallel. Now, yes? R pi prime 1 plus GMRL. Now it becomes multiplied plus RL. This is what the result is. So you know R pi, capital R pi, and you know capital R mu, and therefore you can calculate the two time constants, and FH would be equal to 1 over 2 pi tau pi plus tau mu, that is 1 over 2 pi C pi R pi plus C mu R mu. And if you insert the values that we had already calculated, we had already assumed for the transistor, please do check. My calculations say that R pi is 203 ohms and R mu is 7.79 K. Once again, who dominates? Who dominates? But C mu is a small quantity, C pi is a large quantity. What is C mu? Was 2 puff and C pi was 25 puff. Even then you see, even then this dominates. Isn't that right? Okay. But nevertheless the result comes as 7.71 megahertz. Previously it was 7.88 Miller approximation. So they are pretty close to each other. They are pretty close to each other. I didn't calculate, I didn't solve that quadratic equation. You can also solve the quadratic equation and see how good these values are. You cannot make a generalization, however. Suppose the quadratic equation solution, the exact solution is close to this, you cannot say that method of open circuit time constant is better than Miller. You can't say, because both are approximations. And in some cases this may be better, in some cases the other may be better. But anyway, any of these techniques is used only to estimate FH. It cannot be calculated exactly except when you solve the quadratic equation. Okay? Now, to complete local feedback, we consider the other kind of local feedback which is used, namely an unbypassed emitter resistance, which is a series. The previous one was shunt, now it is a series. And the circuit is like this. Very simple. Now, what should be the source now? Voltage source or current source? Voltage source. Okay. So we say RS, we ignore everything else, and we have a VS. Then the feedback is through RE, and of course we have what should be the output now? It's a series, so the output should be a current. Let's say I0, and this is V0. The output voltage is V0. But our modeling should be in terms of a voltage to current. In other words, the transfer function should have the dimension of impedance or admittance. Admittance. So the transfer function should be an YT, transfer admittance, capital T subscript for transfer. Now, in order to draw the equivalent circuit, you see now since it is possible to take account of Rx, let's do that. Rx would be in series, and there is one more reason why you consider Rs, because if this is an ideal voltage source or nearly ideal, the source resistance would be comparable to Rx, and therefore and since it is easy to take account of this, we do that. So, what we do is, let us say we call Rx prime as Rx plus Rs, alright. Then you can mentally see the equivalent circuit. We shall have an Rx prime, then between this point and this point we will have a Z pi, parallel combination of R pi and C pi, then RE, and we shall have GMV, RL and the inevitable C mu. Okay. So, the equivalent circuit, but it's not as easy to analyze as the previous circuit, because RE carries current from the base as well as from the emitter, okay, from the collector. Alright. So, what we have is Vs equivalent circuit, Rx prime, Z pi, where Y pi is small g pi plus SC pi. Then we have the C mu. This is the collector. The collector sends a current to GMV. This is V pi, V pi, V pi, and this resistance is Re. This goes to RL, and this is our current I0. This is the equivalent circuit. The first thing we do before doing anything else is that we identify this current. This current is obviously V pi over, okay, we can write this as V pi GM plus Y pi, okay, this current. And therefore, I have to find out a relation between I0 and Vs. I will not carry out the analysis, but let us see how to look at it, very critically and find out the shortest path. Okay. Obviously, if I know V0, then I know I0. So, there are two nodes for which the voltages are unknown. Let us call this voltage as V0, this voltage as V0, and suppose this voltage is V1. Alright. Then I can write a node equation here and a node equation here. Alright. Two node equations. Will that solve the problem? No, there is a unknown quantity V pi here also, but you notice that V1 is equal to V pi, this voltage, plus V pi GM plus Y pi multiplied by Re. Therefore, I know V pi in terms of V1. Agree? And all that I have to do now is to write two node equations, one at V1 and the other at V0. Obviously, the node equation at this node is V0 by RL plus GMV pi plus S C mu V0 minus V1 equal to 0. I cannot unfortunately apply Thevenin or Norton. That is my most favorite, because I do not have to write node equation. Unfortunately, I cannot apply here. I cannot simplify. There is a control voltage here. I cannot simplify this. I cannot convert this into a Thevenin source, because it has a lot of complications around it. So leave it peacefully for the moment. And if you have to write a node equation, let us write a node equation. For this node, the equation would be V1 minus Vs divided by Rx prime, that is the current going away, plus V pi by Z pi, this is the current through this, plus V1 minus V0 S C mu should be equal to 0. So eliminate V1 and find out V0 in terms of Vs, and then find I0. I0 is V0 by RL. If you do that, the expression that you get looks horrible, but it can be put in this form: I0 by Vs as some constant k. The numerator becomes a quadratic. Look at the complication. As I said, it is not as easy as the previous one. Numerator becomes a quadratic, s square plus as plus b, and the denominator is also a quadratic. That the denominator would be a quadratic is expected or not expected? There are two capacitors, so it has to be a second order transfer function. There is no question. In the previous case, there was 1 0 S plus Z. There are 2 zeros now. Can there be 3? Can there be 3 zeros? Can the numerator be of degree 3? Yes, it can. Yes, it can. Okay, transfer impedance after all. It's not a driving point impedance. Okay. Now, this looks rather complicated. We don't want to find out K, A, B, C and D and solve the equation exactly. If you solve it exactly, what would be the order of the equation to be solved for omega H? It would be? It would still be quadratic in omega H square. So, it's not too bad. Although it looks complicated, it's not too bad. Only thing is your A, B, K, C and D, they have to be found out. Okay. So, we will go in the shortcut way. We will see what the method of open circuit time constants gives us. Okay. But before that, let us look at the mid-band quantities. It's good to have an idea of the mid-band gain, mid-band input impedance and so on. The mid-band equivalent circuit would be Vs at mid-band. After all, later on what we will do is simply add the pole, add the 2 poles and add the 2 zeros, or simply find out FH. We don't have to calculate the total circuit transfer function at all. Let us look at the mid-band. This is a shorter cut. You see, I did this analysis, wrote down the node equations and so on, because I wanted to show you that there are 2 zeros and 2 poles. We don't have to do this in practice. In the case of analysis and design, all that is required is find out the mid-band gain and find out FH. That's it. Okay. So, and of course, the input and output resistances at mid-band, that suffices. Let's see. This is Rx prime, then you have R pi, this voltage is V pi, GM V pi, and RL. This current is I0, this resistance is Re. It should be obvious what the transfer function is. We don't have to write any node equations or any. You see, we simply write I0 is equal to minus GM V pi. And what is V pi? V pi is Vs divided by the current. The current is Rx prime plus R pi plus wonderful beta plus on Re, but you have to multiply this by R pi. And therefore, Yt is equal to I0 by Vs by inspection. That's why I said in the actual circuit you don't have to make that frequency domain analysis. Mid-band is sufficient. This is equal to minus beta GMR pi divided by Rx prime plus R pi plus beta plus 1 Re. Don't you see that this is approximately equal to minus 1 by Re? Agreed? Minus 1 by Re. If that is so, then what is V0 by Vs? What is V0 by Vs? Minus RL over Re. Didn't we do this earlier? That with emitter unbypassed and beta large, the gain is approximately the ratio of the load resistance to the emitter resistance. In other words, the gain is controlled by 2 external resistances. It becomes insensitive to the parameters of the transistor, and that's a huge benefit. Now, I can also see what the input impedance is. Do I? Input impedance is as seen by Vs, it is Rx prime plus R pi plus beta plus 1 R. So, the mid-band input impedance R in is also known. Well, if you are fussy, you say what the source Vs Rs is, then it will be simply Rx plus R pi plus beta plus 1 Re. Now, the question of output impedance. It is very tempting to say the output impedance would be infinity because there is a current generator. No, this is not. If it was an independent current generator, yes, what you are saying would have been right. one has to actually calculate. Let us see what the equivalent circuit is. Again, once again, there are some tricks that one can apply to simplify the whole thing. To calculate the output impedance, you have to put Rx prime to ground, the input source is grounded, then you have R pi and this is V pi, you have GM V pi, this is RE. In addition now, the output impedance, what do you expect the output impedance to be? High or low? High, and therefore it may be comparable to R0, and therefore R0 now further complicates matters. R0 has to be considered. Okay? Do you understand why? Because it's a series, and then what you have to do is to connect a voltage generator here V and find out this current I. Find out the current I. Okay, this is the circuit. Now, can you tell me what happens if we don't consider R0? Pardon me? It would be infinity.
V pi will be 0.
That's right. And therefore the current generator will have zero current, but it's a current generator anyway, and therefore you shall have infinity. It is instructive to calculate this by inspection without doing anything. You see, what I do is I find that this current, let me use a different color, this current is V pi by R pi. And if I know this current, then don't I know this voltage? What is this voltage? V pi plus V pi by R pi times Rx prime. This is the current? No, I beg your pardon. This is the voltage across this. Oh, this current is also V pi by R pi, and therefore the drop across this is V pi by R pi Rx prime. But there is a big question that I have. What about the polarity? Lower part would be positive and this part will be negative. Please repeat this. Okay, I am going from here to here or here to here. So minus V pi by R pi, this is the current, multiplied by Rx prime. That is what I have done. I have written the total voltage and this is the polarity. So if I know this voltage, then this I shall be simply GM V pi wait a second, I want to write a node equation here. This I shall be equal to GM V pi plus the voltage across this, which is V minus this quantity divided by R0, one node equation. What else do I have to write? Current through? That's right. You see, the current through this plus this should also be equal to I. Isn't that right? So just two equations, and then almost by inspection you can write down the expression for the output impedance. I'll simply give you the exact expression and make some comments because the expression is interesting. The R out is equal to, exact expression is this, R0 1 plus, now you can see that this is, if R0 were not there it would be infinity. R0 1 plus GM plus 1 over R0 1 plus Rx prime divided by R pi 1 over R pi plus 1 plus Rx prime divided by R pi times 1 over Re. This is the exact expression. And if this quantity GM plus, yes, if this quantity can be ignored compared to GM, is there a logic? R0 is very high. That's right. This is the reason. This is normally very small compared to GM, and therefore this is approximately R0 1 plus beta. Now multiply by R pi 1 plus beta divided by RE plus R pi plus Rx prime. Unfortunately, this cannot be simplified further because these three resistors usually are comparable. Okay, and you see that the output impedance is greater than R0, which was expected because it is a series connection. All right. Yeah.
I hope not that the expressions are on out can be written down by inspection.
You hope you cannot do this. You cannot write it by inspection. Okay. Now a student who has not gone through AA204 cannot write down by inspection the gain of that unbypassed emitter resistance amplifier either. It would not make sense to him. But if you do some 10 examples of such similar circuit, you can almost write down by inspection. Your equations will also be mentally written, and you will see the solution. You will see the solution. This is the sign of wisdom. Okay, we close here, and next time we go for calculation of FH.